you for the introduction. Also thanks for the invitation to this very interesting workshop. Indeed, I will be again talking about Whitebox cryptography, but more from a practical point of view, and even more from a cryptanalyst perspective, because I'm a cryptanalyst, and the questions I asked myself were, what can our understanding that we have developed for symmetric key ciphers say about Whitebox primitives, both in terms of attacks and in terms of design. And then also, as a consequence of that, is it possible to actually build something with some residual security in the Whitebox setting that could be practical? Yeah? And in this talk, I will cover some more settings of Whitebox, some applications, very briefly, some existing Whitebox solutions, and point out their problems. And then I will switch to the two primitives that we have designed. The first one is called Space Cipher, which is an AES-based Whitebox block cipher, which you could see as a mode of operation for AES or not, or you can also see it as a dedicated cipher. And the second one is Spm Box, which is a dedicated Whitebox block cipher, which does use AES components as well. And then we have actually implemented those both on server CPUs and client CPUs ARMs. And I will also report those implementation figures for you. This work is based on collaboration with Sony Corporation, Takanori Soga, who were visiting our university for quite a while, and it's where we did most of this work, and on two papers. Yeah? One is ACM-CCS last year, and the other one that was just accepted to Asia Crypt is about SPN Box. So, what is this Whitebox setting? Again, from the point of view of somebody who is doing symmetric cryptanalysis. Well, in theory, what we do, we do this Alice in Bob thing, where we want to send the ciphertext through an unprotected channel. And in the black box, the attacker doesn't see the key, and doesn't see the implementations. A more realistic setting is the gray box. For example, we can talk about side channel attacks here, where the adversary can have some information leaked from the key and or implementations. But of course, in some settings, what we have is the strongest Whitebox setting where the adversary can see everything. Yeah? And here we have kind of a clash of two paradigms. Yeah? One is assuming that the security mechanisms in the field are invisible to the adversary, that we have some trustworthy hardware and software, in that the computer base is secure. But actually, that is the most crucial challenge now. Yeah? Out there, the trust that we have or have not in the computing base. Because we have malware, we have Trojans, and we have memory leakage through side channel attacks. And there are also zero-day vulnerabilities, due to some critical weaknesses in operating systems and software. In here, we have kind of this symmetric key academic world operating under this assumption in designing AES as one of the most important achievements of the this research field, and then here we have the practical hacker, yeah, who is trying to attack our AES in the real world setting, or it could be somebody else, right? So the white box attacker has full control. Yeah? So the white box attacker can do basically everything in technical terms, can debug, can insert changes into the execution flow, can do the dynamic analysis, yeah, everything. But of course, we have to formalize it somehow. Yeah? What is important is, of course, that the adversary does have access to the intermediate variables, yeah, to the intermediate states, memories, the execution flow. And the designer's goal is to attain some residual security, yeah, in this setting, practically speaking. Of course, theoretically speaking, we can talk about, you know, perfect obfuscation, but practically speaking, it would be very nice if we could have at least some residual security in this white box setting. Yeah? And that's something I'll be talking about. And of course, we cannot protect against every adversary. So we'll have to pick something. And as Mathieu mentioned in his talk, there is this difference between weak white box security and strong white box security that we kind of hope to be able to attain, maybe with some dedicated construction. Of course, the ultimate goal would be to design an AES implementation that would attain both. Yeah, that would be really great. But for the time being, it would be already nice to have something that just satisfies the weak white box security, meaning that it should be difficult, given the full access to the white box implementation, to recover the cipher's key, yeah, from this implementation. And then, on top of that, we can add, maybe at some point later, the difficulty of inversion. What are some applications, white box crypto? Well, there are numerous applications, obviously. Recently, people have been talking about content distribution, which is also probably the origin, yeah, of white box crypto, where possibly it all started, is the DRM. And here we have some server that is distributing content, and we have some client who is reading the content. Now, what we can do, we can implement the same encryption in two different ways, yeah, on those two platforms. On the server, we can assume more security, possibly, than on the client side. So what we can do, we can actually implement a black box version of an algorithm on the server. Yeah? You can think of it as a black box AES or black box encryption of any source. Now, here, what is really important is the security of this primitive in the black box as a standard cipher, yeah, and the security of the implementation. For example, it could be subject to some gray box attacks, such as cache timing. So your cipher should ideally be such that you could protect it against some gray box attacks as well. And then on the client device, you have the white box implementation, which can be very different from what you have on the server side. And it may be possible that this white box implementation is less efficient, yeah, on the client, because client only deals with one stream of data. Yeah? The server deals with millions, possibly billions streams of data. So the black box implementation should be quite efficient, and the white box implementation may be a bit slower. So those are some premises we're talking about here. In a popular recent application is also the host card emulation. For example, there is an Android versions, this functionality is supported. What it basically says is that you want to do secure hardware in software. Yeah? So you want to replace your secure hardware with a call to a software library. And that is, of course, something that will be coming more and more. And it's also a setting where often the white box security demand arises. Yeah. Here we have a similar setting, where we can actually have different implementations on the server and on the client, similarly to DRM and content distribution. There are a lot of other applications, obviously. I'm just mentioning some of them. For example, mobile banking, where you have a app and you want to authenticate your app to the bank, to the server. One possible application for governments and military who might be afraid of more powerful governments taking over the computational base there, using the CPUs, the software. And it can be seen also as protection against mass surveillance. I think there is a nice Crypto 16 paper which will be presented next week on big key symmetric encryption, and it also goes towards protection against mass surveillance. Now I will give a very quick overview of some approaches to build practical white box implementations so far. And of course, I will start with the seminal work by Chow et al. From 2002. This work tried to build a protected implementation of AES based on tabulation. So, in terms of sessional attacks, you can see this as masking, but with a static mask, in many ways. And then they also discuss some external encoding, where you add some secret permutation before and after the cipher, which does pose some difficulty for some attacks. Using this idea, a lot of other implementations emerged, primarily for AES. But the sad thing is that all of them have been practically broken. And I think all of them were actually broken in the static sense, that if you have access to the tables, you can break the schemes. So you can extract the key, or you can at least decompose the table. Those were, of course, more or less ad hoc solutions with some limited fundamental base, but quite seminal, because they pointed out the direction in which it could go. It's also important to mention that most of those implementations are insecure even in the gray box setting. I think we'll have a talk about DCA later today. also DFA, I think, correspondingly by NXP and RISQ, who will talk more about that, how this approach is vulnerable even to very basic gray box attacks, not to mention the white box setting. Then in 2014, there was ASASA, construction, a dedicated white box construction, basically a block cipher, nested SPM, that was using a combination of affine or linear transforms and nonlinear transforms, secret S boxes, to build a weak white box scheme and also a public key scheme, actually. But most of the instances here were also practically broken. At least you can do table decomposition. If you want to use this approach, you would need at least 12 layers of ASASA. Maybe more, because this approach definitely needs more analysis for the underlying problem. Now, a very rough summary of what we have so far. We have Chow et al.'s approach, where we have key recovery and decomposition. And we have the ASASA approach that is a dedicated approach. So maybe it's secure as black box cipher, but in the white box setting, it's rather insecure, at least with lower number of rounds here. So the question is there any comparable approach with some actual security in the white box? And the challenge is now, to summarize, to build something with black box security, in the sense of key recovery and indistinguishability, so in the sense of classical symmetric-key security of a block cipher, for example. To build something that would have a white box implementation, at least secure against key extraction, possibly against compression attacks, and would be efficient. What does it mean? Compact and fast in the black box, and not too time-consuming in the white box. And this is the first cipher that I will present. So it's a dedicated cipher, but it's based on the AES. So AES is inside. What is the twist here? The twist is rather easy. It's rather easy to grab. So instead of trying to implement AES with a lookup table, where you incorporate some encoding before and encoding after, you consider a table that represents the full AES call, but truncated with respect to inputs and outputs. Yeah? So you input NA bits here, and you get some bits out. And here you do the full AES call, inside. Now, based on that, and I will show you in a second how this is attainable, one can build at least something that corresponds to the challenges over here. Some other design goals that we had were that the key recovery problem for the cipher, is actually based on some fundamental problem. And we managed to do that. So the key extraction security of this primitive would reduce to the key recovery of AES. We didn't want to use any external encoding, and as an additional feature, we wanted to allow different users with exactly the same key to be able to have Whitebox implementations of different sizes. Yeah? In a bit more detail, in the black box, we want the cipher to be a classically good block cipher, and we can design symmetric-key ciphers now. It's quite industrial. Then we want security in the Whitebox in the sense of key extraction security and incompressibility. Here, the notion that we use is called Space Hardness. It's linked to the incompressibility notion from Sec 13 that you just presented, and to some notions in the big key symmetric encryption paper, which will be presented next week. So what is this space hardness? Space hardness basically says that it's infeasible to efficiently compute the encryption, decryption with some good probability given a subset of the table that is used to implement your cipher. Yeah? And the parameters M and Z quantify this. So M is the size of this part of the table that you want to use, and Z is the probability that you're actually able to compute a ciphertext, for example, given plain text. Though there are many other variants of this notion as well. Now, back to the design. What we do with this truncated AES, we put it into a target-heavy file-to construction, where this would be truncated AES, basically. And then we run this instruction for many rounds, and the number of rounds is basically defined by the level of space hardness that we want to attain. So this is what's inside. It can be also any other cipher, of your choice, but it can be AES 128 or 256, whatever makes you happy. Now, we chose rather high numbers of rounds for our examples, but of course, many other parameterizations are also possible for this. But we focus on 4 parameterizations here, 8, 16, 24, and 32, where the number represents the exponent in the table size. So, for example, space cipher 24 would use tables of size approximately to the 24 entries for implementation. Now, these are the numbers of rounds that we use. And this is to attain very high level of resistance towards space hardness, towards compression attacks. It's not related to the black box security of the ciphers. You can easily go down with those round numbers quite a bit, up to factor 10 actually, without losing much black box security. So security as a block cipher. Now, it's fairly easy to see that the key extraction of this construction reduces to the problem of AES key recovery. So it's just a subset of attacks of AES the adversary can try to apply. Because you deal with part of the full AES computation. Yeah? So your input is restricted to a subset, and your output is restricted to a subset. In terms of space hardness, those are the claims. At the level of z equal to 2 to the minus 128, yeah? So this is the probability of success in your compression game, which is very conservative probability. Those are the claims here that, for example, space cipher 24 cannot be compressed to a representation that consumes less than 100 megabytes. Again, you can play with those parameters. As for the security in the black box, here we have performed evaluation against many attacks. This is a basic summary of that using symmetric-key techniques, using standard cryptanalysis. In the sense, we use to analyze AES itself. So we have differential linear cryptanalysis, impossible differentials, and so on. And as you can see, number of rounds is quite conservative in the number of rounds that can actually be distinguished. And this high number of rounds is mainly due to the conservative requirement on the space hardness, namely on the z of to the minus 128. Okay? Any questions at this point? Yeah.
Yeah, so for this implementation, a round is a call to this truncated
Yes.
AES, right?
Yes.
And that should be a whiteboxed AES?
So in the black box setting, you can call the black box implementation of AES because it may be more efficient to do that, especially if you have bigger tables. Yeah? So you only have to store 128-bit key in the black box setting to be able to implement this cipher. But in the white box setting, you have a table. In the white box environment, on the client, you actually do table lookups.
But since we do not know how to make a secure whitebox AES, will that then affect the security of the scheme as well?
No, so it's unrelated, yeah.
Okay.
Because the security of this construction, in terms of key recovery, for this key over here, that is just inside, is based on the classical security of AES. Of course, now if you define an equivalent key as this actual table, then we cannot protect in the white box setting from any code lifting, because code lifting is always possible.
So in particular, you're not making any claims of CPA security?
Just a block cipher.
As a white box, in a white box?
In the white box setting, we make two claims. One claim is key extraction security, and the second claim is space hardness. But other notions can be used, yes, to analyze this.
In particular, do you think it's broken with a chosen plaintiff style?
No, I don't think broken in which sense?
So if I don't understand completely the construction, but if it's a bicycle network, right?
Yes.
And you see the tables,
Yes.
then you can also reverse it and decrypt, right? Knowing the tables.
Yes, you can always decrypt, yeah.
So then that means that in particular it's insecure. Like see a cipher text and see a white box. can decrypt.
Yeah, so this cipher is a weak Whitebox cipher, so it's not strong Whitebox cipher, yeah, which would be the public key scheme. Right? But in terms of the weak Whitebox security, this is your lab. Yeah.
I don't get what you take your huge number of terms. You say it's for Space Hardness, but you can tune the Space Hardness with the NA parameter, basically.
Yeah, with the NA parameter.
You get an efficient,
of course,
less efficient encryption.
So, but if you have just one table, let's say, yeah, then the maximum space hardness you can attain is the size of this table.
Yeah, but if you take greater NA, so the table is greater.
Yeah. So if you can afford that, of course, you should do that. But for the settings where it's hard to do, yeah.
It's because you want to have a smoother granularity?
Yes, of course, yeah. And it's just 4 points, what shows that. Yeah, there are obviously many points in between as well. Yes. But of course, in the sense of big key concept or weak Whitebox security, one should go as high as possible with the table size. It makes it harder and harder to extract the key in the real world environment. Yeah. But right now, if you just implement the EES as black box implementation, then you only have to extract 128 bits. So this is basically your leverage. Okay. The next construction is called Spm Box, which is even more dedicated Whitebox cipher. It's a nested substitution permutation network where you have 10 rounds of the overall SPM, and inside the S boxes, which are 8, 16, 24, or 32-bit, again, just for granularity, you have a dedicated block cipher on this block size. Okay? And this is a block cipher that is using AES components, such that in the black box setting, where we have access to a server CPU with AES and I, it's fast. Okay? And we actually did perform this implementation. Now I will give a couple of more details of this cipher. So we have some MDS matrices in the outer cipher. Of course, different for different sizes of the inner cipher. And those are the matrices. Most of them are involutions, actually. M32 and M16 are the ones using Anubis and Kazakh ciphers. And M8 is involutory anamorphic Cauchy matrix from FSC15. And then what you do for the S box is actually to design a dedicated small block cipher. And those are the matrices that we use for that, and we do use the AES S box as the non-linearity. Again, this is to speed up the black box implementations of these ciphers. And as you can see, the constants in the matrices are chosen such that they're subsets of the mixed column, the AES mixed column. That it is possible to reuse AES and I instructions. Now, some claims towards space hardness, and we do define two overall notions for space hardness is weak space hardness and strong space hardness. And I will not be talking about strong space hardness, but you can also read it in the paper at some point. Here are claims as regards weak space hardness, which basically says, give me an encryption of the channels with as low number of entries from the table as possible. And then we do consider two subsettings there. In one setting, before the plaintext is given to the adversary, before the challenge is given to the adversary, it ever can copy tables non-adaptively, and in other setting, the attacker can copy tables adaptively. Okay. But of course, not after the ciphertext the plaintext was communicated. Okay, now I will finish off with an implementation study. We implemented both Spm Box and Space in the black box and in the white box. In the black box, it was on Intel Skylake with ES9. In here, as you can see, we can attain performance of several dozen of clocks per byte, cycles per byte. And as you may remember, until very recently, AES was 20 cycles per byte. And then 15, around 15, and then the ES9 came out. So this is quite an okay performance, actually. This can be optimized. Again, the number of rounds we choose here is mainly driven by the claim on the space hardness. And so it's again at the level of to the minus 128 probability of success. So if you are fine with a slightly higher probability of success, let's say to the minus 64, which should be okay in practical settings, then you can drastically, well, up to maybe factor 2 reduce number of rounds, which will automatically make implementation faster. Space is a bit slower in the setting, but we also have a bigger buffer for improvement. So up to factor 10, depending on your space hardness requirements and concrete variant. What do we have in the Whitebox setting? Well, we did implemented both on Intel Skylake and on ARM v8, because ARM v8 is probably one of the more likely client hardware platforms for this type of crypto, and those are the numbers. So again, you have performance from several dozen to several hundred cycles per byte. Yes?
With that size tables, I've got to ask, do you actually have a machine with 50 gigabytes of semiconductor memory, or is that doing disk lookups? Or?
This one is given to the operating system. So what the operating system does, we don't know, but physically, we don't have 17 gigabytes of memory, I think, on that particular machine. Okay. Those are clear, yeah? Those are RAM. And as you see, we didn't perform it on ARM, yeah? With several gigabytes. Okay, so those are the performance numbers. To conclude, yeah, we have had a look at what cryptanalysis and symmetric-key techniques we have to analyze and design ciphers can tell us about Whitebox encryption, and we have actually come up with two dedicated designs that attain weak Whitebox security in the sense of incompressibility and key extraction security. Space Cipher and Spm Box. And those are just examples of the paradigm where you use block cipher inside your Whitebox cipher as a building block, and then you can implement this underlying cipher differently depending on your setting. So if you're in the black box, you can do more efficiently and compactly. If you are in the white box, you can just do table lookups at the level you prefer. Yeah? So for as much memory as you have, basically. And then it's possible to come up with different variants of those ciphers, basically by reducing the number of rounds if you are satisfied with a lower claim on space hardness. And yeah, it's also possible to prove many more things about such constructions. So you have a reference to our Asia Crypt paper, but also to a big key symmetric encryption and an imprint paper about wide key and wide block by using the same idea of ours and do some refined theoretical analysis. Okay, that would conclude it. Thank you so much.
Questions?
Yeah, so yeah, I think it's a really interesting approach. So for other cryptanalysis, is there, you have performance figures? Is there an implementation or a challenge available such that other people can try and break it?
So first of all, it's very easy to implement. Because you can just call AES.
Yeah, but you already implemented it, right?
Yeah,
you showed numbers. So is this implementation available, or?
It's not public, but yeah, it can be made public. So
yeah, I think that would be of interest.
Right. So the analysis here is as hard as breaking AES, basically, in terms of key extraction. There might be things in terms of space hardness, yeah, that one could analyze, yes.
The questions? Questions? So let's thank Andrey again.